Let us understand how do we sketch the graph for a rational function. In this video, I'll walk you through the whole algorithm step by step, making each and every point absolutely clear. Let's enjoy the video. I'm Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll understand in details curve sketching of rational functions. Example before us is f of x equals to 2x squared minus divided by 1 minus x squared. I'll walk you through the algorithm for curve sketching, which is for rational functions, and then we'll try to understand each and every part in details. The video is going to be long. It will provide you complete details and concept of sketching. So let's begin by saying what all do we need. So when I say algorithm for curve sketching means steps to be followed. So let's list our steps. For a rational function, we are mainly focusing on rational functions. Rational functions are unique that they have asymptotes, right? And so, finding asymptotes and behavior near asymptotes become critical. All of these steps are similar to which could be followed for other functions, okay? So, well, to begin with, step number 1, I would say, is to get the basics about the function itself, which include domain. So when you are finding domain, you have to find restrictions, and in rational function, those restrictions are basically because of holes or vertical asymptotes, right? So we'll say restrictions. In this case, the restrictions are vertical asymptotes. They could be holes also at times, right? So that is first part. Second, what you need to do is to find intercepts. So you find x-intercept and also y-intercept. And then, once you have this basic thing, there are some special properties which you could look into. And the special properties in this particular case, as I said, are vertical and horizontal asymptotes, right? So, behavior near asymptotes. So, which includes both vertical asymptotes and horizontal asymptotes. Once you've done all this, we can look into the analysis of first derivative and second derivative. So, first derivative analysis, which will give you increasing, decreasing, and also extrema. And lastly, we need to figure out what is the second derivative analysis. That gives you concavity and point of inflection, right? And once you've done all this, we can club all the information and sketch graph. This is what you call curve sketching. Now, every time when you look at the function, there could be some very special things. For example, here, I find one thing very special is to look into symmetry. Right, so we can also look into the symmetry of this function as this seems to have a symmetry, right? So, well, what I'm trying to say here is, apart from the normal algorithm which I've discussed here, there could be some other points. For example, some key points, right? We can just find value of function at x equals to some other values rather than just zeros, right? So this is kind of overall view of what you should be looking at before sketching the curve, right? So before curve sketching, you get to know all those things together, right? Now let's look into the first part, which is the domain of the function. So we are given the function f of x equals to 2x squared over 1 minus x squared. So definitely that 1 minus x squared, which is in the denominator, is not equal to 0. And that gives you the idea that x is not equal to plus minus 1, right? Square root of 1 plus minus. So that becomes the restriction, right? So that gives you two things right away. And first thing, which is that domain is what? Domain is that x belongs to real numbers, where x is not equal to plus 1 or minus 1, correct? 2 points. And second, it tells you that since there is no whole here, right? No common factor, we can write they have a vertical asymptote at x equals to 1 and at x equals to minus 1. So there are two vertical asymptotes, right? Both at plus and minus 1. Well, you can also find the intercepts. Intercept is what happens when x is 0 or when y is 0, right? In this particular case, we can see that intercept, if I put x equals to 0, in that case, what is f of 0? Well, f of 0 is 2 times 0 over 1 minus 0, which is indeed 0. So in this case, we have the graph going through the origin, right? That is to say that 0, 0 is your x-intercept as well as your y-intercept. Is that clear to you? Perfect. Correct. So we got some basic information here about the function. Let's continue. Since we found what the vertical asymptote is, we need to actually figure out what is the behavior near the vertical asymptote. So let's sketch what we have got, the information, right? Let's put it together. So the graph of this rational function, we see that there are two vertical asymptotes. One is at plus 1, the other one is at minus 1, right? So these are the vertical asymptotes. We can write them as x equals to 1, and this one here will be x equals to minus 1, right? We also found that the graph goes through the origin, right? Now the idea is that what is the behavior? Does it go, when we are approaching minus 1, does it go towards negative infinity or positive infinity when approaching from left or right? That is the whole thing, right? So this is what we call behavior near asymptote, right? So let's figure this out. We have that as x approaches minus 1, f of x or y approaches what? This is what we need to figure out, right? So it could approach minus 1 from either left side or from the right side, right? So when we write minus 1 minus on the top, then we are saying when it is approaching from the left side, is it? You get the idea? So when x is approaching from the left side, so what you can do is you can place a value here, calculate, right? So if I put f of, let us say a value which is on the left of -1, let us say -1.1, is it okay? If I put this value, then what do I get? So numerator is positive, right? This is positive because we have 2 times x squared, no problems. As far as the denominator is concerned, 1.1 is more than 1. When you square it, we get a negative value, right? So we find that this is negative. Since it is negative, then the function will go to negative infinity. Do you see that? You don't have to evaluate. That's what I'm trying to say. You do not have to evaluate. You can sometimes use calculator and evaluate, but not required. So we're trying to say that it approaches negative infinity, and that is how we are going to show it. Is that clear to you? Perfect. Now, let's see what happens when we are approaching -1 from the right-hand side, right? In that case, you can substitute a value, which is -0.9, which is on the left of -1, correct? So if this x value is less than 1, then the square will be less than 1, right? And therefore, definitely, we have something positive over positive, and we approach a positive infinity, right? You're approaching infinity. The only thing is you have to figure out whether it is positive or negative infinity. Do you see that? So when x is approaching 1 from the positive side, in that case, we found that f of x is approaching positive infinity. Is that clear to you? If not, we are again going to do what happens at 1. Let's analyze this. Right? So what will you do? Check what happens when x is approaching 1 from the left side. This is from the left. Is it okay? So that means substitute a value which is, let's say, 0.9. It is to the left, right? So in that case, what happens to f of x? F of x approaches a positive value, right? And therefore, it goes up here. Do you understand what we are trying to say, right? Once more, x approaches 1 from the right-hand side. Value to be substituted is 1.1, and f of 1.1 is negative. Do you see that? Correct? F of 1.1 is negative. So that means when x approaches positive 1, f of x approaches negative infinity. So you're approaching like this. You see that. So that becomes a behavior which is shown with the help of these arrows. Correct? Don't confuse yourself with that arrow. This was for the equation, right? Let me erase this now. Okay, you get the idea, right? So we figure out that the equations which are x equals to plus minus 1, the vertical asymptotes, we know now the behavior, right? So that is how you have to get the behavior near the vertical asymptote this time. Perfect. Now let's move on and find the horizontal asymptote for the given function. Perfect. I hope you are understanding all the concepts, right? Well, in case you want to learn from me, you can always send an email to learn directly from me. And you can also check our website for the latest updates. Many of my students are doing extremely well. Some are right there on top of their class, getting awards and scholarships like Akshat.
After attending university. The winner of this year's Certificate of Achievement Schulich Leader Award is Akshi Kandivani.
Great. Our student, Akshat, gets highest marks and the most prestigious Schulich Leader Award. You can be there. Join our classes and excel. Now let's continue with horizontal asymptote. So far we figured out the intercepts, domain, and the vertical asymptote behavior near the vertical asymptotes. Now, sometimes you might just struggle to find the horizontal asymptotes. Now, in this case, we do see that degree of numerator and denominator is the same, right? In that case, we have a horizontal asymptote, which is ratio of leading coefficients, right? In this case, it'll be 2 over minus 1 or minus 2, right? Which basically is the ratio of leading coefficients. That is a shortcut of numerator and denominator. But how do we do it algebraically? That is what I'll show you in a minute. So we're given the function as 2x squared over 1 minus x squared. So let me factor out x squared from denominator. So when I factor out x squared from denominator, I get 1 over x squared minus 1. We can cancel this, right? So we get 2 over 1 over x squared minus 1, right? Now think what happens when x approaches a large value. In that case, 1 over x squared approaches 0. And so the whole function f of x approaches what? It's a concept of approaching, right? So it approaches 2 over minus 1 or minus 2. You get the idea. And therefore, we have the horizontal asymptote, which is y equals to minus 2, correct? Is that clear to you? That is how we are going to find the horizontal asymptote. Now we need to figure out what happens when we are approaching on x approaches negative infinity or positive infinity, right? Is it more than minus 2 or less than minus 2? This is what you have to figure out. So when you say approaching from above, we could approach from above or below. You get the idea, right? We can approach from above or below. Okay. Now there are many ways to do it. Best and easiest way is use your calculator and then substitute a value. Let's say f of minus 1000, right? So if you put f of minus 1000 here, what value do you get, right? So let's calculate and find decimal value. So we have 2 times 1000 squared. The numerator is positive, right? So it is 2 times 1000 times 1000 I'm writing, divided by, within brackets, 1 minus 1000 squared, right? Bracket close equals to. And the decimal value which I get is minus 2.002. So we get a decimal value which is more negative. You get the idea. We get a decimal negative, right? So which is actually less than minus 2, right? So it becomes from below. Makes sense. Another thing you will notice is when you look at your vertical asymptotes, and we just found that the horizontal asymptote is at x equals to minus 2, right? So let's complete here itself. At minus 2, we got our horizontal asymptote, right? Let me write y equals to minus 2 as our horizontal asymptote. So from here, you can also see you will be approaching from below. Do you see that? It makes sense. It is kind of a check. It is kind of a check, right? And the other graph has to be like this. Makes sense because this is your x-intercept. And there's only one x-intercept. So that means it is going to be positive, right? Perfect. So that becomes your graph in a way. So you have your answer, but algebraically you should verify. That's what I'm trying to say, right? Similarly, when you find the value of f of 1000, in that case, you'll get a value which is greater than minus 2. That means you approach from above, right? Oh, sorry. So in this case also, on this extreme, you will get less than minus 2. So here also, you are approaching from below, right? So in both the cases, you approach from below. And therefore, on the graph which we just created, it will look like I've shown here, right? Is that clear to you, right? So that is the behavior near infinity plus and infinity minus. We are approaching horizontal asymptote from below, right? Is this clear to you, right? So I will say here, once you get this information, connect with earlier learnings. Perfect. Let's move on. So we did observe that this function seems to be even in nature. So we are checking the symmetry of the function, right? To check the symmetry, we'll find what is f of minus x. If I substitute minus x, I get 2 times minus x whole square over 1 minus of minus x whole square. And that gives you 2x squared over 1 minus x squared, right? Which is same as f of x. And since f of minus x is equal to f of x, we see that we have even symmetry. Is that clear to you? So this is also important because it really means that our graph is symmetric about the y-axis, right? So the left side of y-axis will overlap the right side of the y-axis. You get the idea, right? So we are looking at even symmetry, right? Strictly speaking, at this stage, you are in a position to sketch your graph. So let me do it here, small but correct, right? So we are saying that we have a horizontal asymptote and we have 2 vertical asymptotes, right? And the nature of the graph is that in between, it has even symmetry going like this, and here it is like this. Is that clear to you, right? These values are at minus 1 and plus 1. This is, of course, at origin, and that is y equals to minus 2. So that strictly is your graph, right? But anyway, we'll continue and analyze the first and the second derivative. Even if you sketch the graph at this stage, you actually get quite good marks, right? But you need to do analysis of first and second derivative to get full marks. That's the whole idea. So let's find the first derivative of this particular function. So we'll use the quotient rule, right? So we have 1 minus x squared whole square in the denominator. Numerator derivative of 2x squared will be 4x times the denominator 1 minus x squared minus 2x squared times the derivative of denominator, which is minus 2x, right? Let's simplify this. Open the bracket. So we get 4x minus 4x cubed minus, and minus becomes plus 4x cubed over 1 minus x squared whole square, correct? And 4x cubed cancels, so we get 4x over 1 minus x squared whole square, right? So clearly from here, we have a very critical point, and that is that the derivative is equal to 0 at x equal to 0, right? So that is a critical number. The whole idea of analyzing the first derivative is to find increasing and decreasing intervals and also extrema, right? That's very important. So let us analyze this particular point, x equals to 0, on either side. Well, we do see that the denominator is 0 for plus and minus 1, right? So those are also kind of critical points where the derivative does not exist, right? And those points could help you to understand increasing and decreasing behavior. So we do see the other critical numbers at x equals to minus 1 and plus 1, which are the vertical asymptotes, right? Strictly speaking, the domain is divided by the vertical asymptotes, right? So while analyzing the first derivative, it's a good idea to analyze all these points. So I normally do not consider only zeros. I consider the points where the derivative does not exist. Derivative does not exist at plus and minus 1, and therefore I am taking those. I am showing them with a dotted line clearly that they are not in the domain. Is that clear to you? So these are the three critical points for me. And in each one of them, I'm going to take a test point, right? So test point on the left side of minus 1 could be minus 2. In between, we can take minus 0.2 or half. And here I can take half, and here I can take 2. And our derivative is 4x. So one part is 4x. 4x is going to be what? Well, 4x is going to be negative when we put in the negative values and positive when positive values are placed. The denominator is positive always because it is 1 minus x square whole square, right? So it is always positive. Now from here you clearly see that the first derivative will be what? Well, the first derivative will be negative, again negative, positive, and then positive. Now negative and positive clearly gives you absolute minimum, right? So when the derivative is negative, it means the graph is going downwards, right? Means downwards, correct? Up and up. You see that. So we now know the behavior. These are the decreasing intervals, right? So we can say it is decreasing within the intervals from minus infinity to minus 1, right? And also from minus 1 to 0, and is increasing thereafter, right? So from 0 to 1 and from 1 to infinity, correct? So we found one very important part, increasing, decreasing interval, but it is kind of important to take vertical asymptotes. So many times students neglect it. That may cost them marks, and useful information more important, right? The other point is, at this particular point, we have a minimum, right? Local minimum. So at this point, at x equals to 1, we see that behavior changes from decreasing to increasing. So at 0, the value is 0, and that is our local minimum, right? Perfect. So now we can verify from the graph which we had drawn, we do have a local minimum at origin, and the graph is decreasing and increasing intervals are also matching. On the left side of y-axis, it is decreasing, right? On the right side, it is increasing. Clear? So we have clearly analyzed our first derivative. Now we move on to the second derivative. Now to find the second derivative, we have to begin with the first derivative, which was what for us? First derivative was 4x over 1 minus x squared whole square. So that is our first derivative, right? So let's find the second derivative now. So in the second derivative, what happens? Quotient rule once again, right? So we have 1 minus x squared whole square to the power of 4, right? Okay. Derivative of 4x is 4. So we get 4 times 1 minus x squared whole square minus 4x times derivative of this function, which is 2 times 1 minus x squared, times the derivative of this, which is minus 2x. Get the idea, right? So this becomes the second derivative. Let's try to simplify. In the denominator, we have 1 minus x squared to the power of 4. And in the numerator, we have 1 minus x squared whole square as common, and 4 is also common, right? So we can write 4 times 1 minus x squared, right, as common. So we're left with 1 minus x squared and minus x times 2 and minus 2. So when you multiply these, the minus and minus becomes positive, right? So we have plus 4 is already taken care of. 2 and 2 is 4. So 4x square, right? Yeah. Because this x and that x gets multiplied. So we have 1 minus x squared plus 4x squared. So the second derivative can be now written as equal to 4 times. Now this 1 minus x squared will get cancelled with the denominator, right? And we get 3 here, right? So in the denominator, I'm writing 1 minus x squared whole cube. And within the brackets, we have 1 plus 3x squared. You get the idea. Now 1 plus 3x squared, which you see in the numerator, is always positive. Correct? So in this particular case, you see that the critical point is on either side of x equals to plus and minus 1, right? And therefore, we have to check the concavity on either side of plus and minus 1, right? So what do we notice here is that the value of x, the absolute value of x, if it is greater than 1, then it is negative, right? So what we notice here is that if absolute value of x is greater than 1, in that case, the second derivative, because 1 minus greater number, right, and cube will make it negative, will be less than 0, correct? So if it is less than 0, it will be concave down. And when absolute value of x is less than 1, in that case, the second derivative is going to be greater than 0, means concave up, right? Positive. You get the idea. So the nature of the graph is that away from plus and minus 1, right, it is concave down. So let's check. So do you see it is concave down, right? And that is up. Do you see that? So from here, we just confirm concavity, right? So with all this combined together, we can now sketch the graph. Is this clear to you? Perfect. Once again, in case you want to learn from me, you can always send an email on the address given. Our students are doing extremely well, right? You can also achieve the same level. Now let's look into sketching graph and analyze, rather summarize what all we learned, right? So we got the x and y intercepts since the graph goes through the origin, right? And we got the local minimum, which is also at the origin, right? And we also saw that the function is decreasing. Let's check once again, right? Vertical asymptote at x equals to plus and minus 1. Horizontal asymptote at y equals to minus 2, right? So with that, let me just sketch some part of it. And also it has even symmetry, right? And there you go, we have a horizontal asymptote, which is y equals to minus 2, right? And these are your vertical asymptotes, x equals to 1 and x equals to minus 1, right? In between, it is concave up with local minimum at 0. And here, It is concave down, right? So you can write all the properties which you learned, right? Even symmetry. Approaching, right? So when x approaches minus 1 from minus side, y approaches negative infinity. When x approaches minus 1 from right side, y approaches positive infinity. When x approaches plus 1 from minus side, y approaches positive infinity. And when x approaches plus 1 from the right side, y approaches negative infinity, right? As far as horizontal asymptote is concerned, when x approaches negative infinity, y approaches from below, right? You could also write from below means y approaches minus 2 more negative, right? When x approaches minus or plus infinity, same behavior. So in both cases from below, right? Makes sense? And then we know it is concave up when absolute value of x is less than 1, and concave down when absolute value of x is greater than 1. Beautiful way of writing, you see that. And we got domain, range, and everything. So that is the final graph of the rational function, fully labeled, right? Indicating the behavior near the asymptotes, all asymptotes identified and labeled. So that gives you 100% marks for such graphs. So once again, I hope this sheet completely summarizes what you really need an algorithm, what type of algorithm you really need to sketch the graph of a rational function. Right? So it is almost same for any rational function. So with that, we come to an end, and I hope it was a learning experience. Feel free to write a comment, share your views. In case you like and subscribe to my videos, that'd be great. Looking forward for your emails in case you want to learn directly from me. Also, explore the website for more videos, fresh ones coming up soon. Thanks for your time and all the best.